In our previous videos, all of the calculations we've done have been on something called an ordinary annuity. We're doing the accumulation phase of that ordinary annuity. And during the accumulation phase, starting at zero balance, and we're working up to some future value at the end of the annuity. And what makes the annuity different from regular compound interest, as we saw, is those payments get made in every period. When an ordinary annuity, those payments get made at the end of each period, so the last payment is made at the very end of the investment. You make that payment and you're there, you're done, you've reached that future value. There's no interest actually earned on that last payment because that's the end of it. There's another type called annuity due. And in an annuity due, those payments get made at the beginning of each period. And what that means is that the last payment is made and it sits there for a full period before the end of the annuity. So that gives us one period more interest. So if we're making payments in and we're looking for that future value, we have to adjust that future value by a factor for a single period's worth of interest. That single period's worth of interest is going to look like this. 1 plus r over n, where n is our number of periods in a year. R is our rate. So let's look at a couple of examples of this. Let's say that Kim is 24 and wants to invest $200 each month at, let's go 10.3% interest until age 67 in an annuity due. So I'll find that future value. So the key word here is annuity due. If we're not told specifically that this is an annuity due, we assume an ordinary annuity and we calculate just like we have in the previous videos. Being an annuity due, to find that future value, it starts out exactly the same as an ordinary annuity. We have our payment, $200, times, there's 3 open parentheses for that compound interest of an annuity factor. 1 plus r, our rate, is 10.3%, so that's 0.103. Payments are made monthly, each month, so n is 12, close parentheses. The power of 12 times, we need our years here. We have 67 and 24. 67 minus 24 gives us 43 years. Then minus 1, close parentheses, divided by, open parentheses, our rate of 0.103 divided by n of 12. Close the parentheses and close them again. And now we have to multiply by that correction factor, that one period's worth of interest, which is 1 plus r is going to be 0.103, n is 12 divided by 12, like that. So we got 200 times 123, 1 plus 0.103 divided by 12, close parentheses, to the power of 12 times 43, we'll close that parentheses out. Remember, we got to arrow out of our powers on some calculators. Minus 1, close parentheses, divided by open parentheses, 0.103 divided by 12, close and close. Now we got to do that extra factor, so times, open parentheses, 1 plus r is 0.103 divided by 12, close the parentheses. We get 1,910,105.19. So the future value is $1,910,105.19 on that annuity due. Now, if we backed it up, I'm going to divide by that correction factor for an annuity. It makes a difference of 1 period, 1 month's worth of interest here. You can see it makes a difference of about $16,000 to $17,000. This $1,893,849.64 is what the balance would have been in an ordinary annuity. So that's the advantage that annuity due. It gives you 1 extra period of interest. You have to make the payments 1 period earlier, though, as well. If we want to go back the other way, let's find the payment required to achieve a future value in an ordinary annuity. Let's say that Alex wants $400,000 for retirement in 25 years. How much should Alex invest each month in a 9.5% annuity due? Again, that phrase annuity due came up, so that tells us we're making the payments at the beginning of each period, so we do have to have 1 extra period's worth of interest. So what this means is in order to calculate our payment, we first have to start with our initial or given our desired future value, $400,000. And we have to divide by that factor for that extra month's worth of interest. So 1 plus our rate of 9.5% is 0.095. Divided by, this is paid in each month, so N is 12. Giving us $396,858.21. So there's that $3,150 interest about that's earned in that last month. We have to take back out of it. This is the number that we're going to use as the future value calculation because we're going to use the same formula we used for an ordinary annuity. Now you'll notice I didn't clear my calculator. I'm going to leave that in my calculator. And when I enter it, I'm just going to go ahead and hit divide, and so it uses that previous answer so I don't have to re-enter it. So I don't lose that information in rounding off there. So my required payment here is equal to that future value right there, $396,858.21 divided by 1, 2, 3, 1 plus my rate of 0.095, and it is monthly, so 12 months a year, to the power of 12 times 25 years minus 1, close parentheses, divided by, open parentheses, 0.095, divided by 12. Close and close. So again, if you typed in the 396,858.21, you might get a slightly different answer than I'm going to get here, because I left it in the calculator, so I'm using it unrounded. So divided by 3 open parentheses, 1 plus 0.095, divided by 12, close parentheses, to the power of, in my parentheses here, 12 times 25 for my exponent. I arrow to get out of it, minus 1, close parentheses, divided by, open parentheses, 0.095 divided by 12. Close and close. And so I need $325.54. Chances are, if you wrote this down and typed it in instead of continuing with it in the calculator like I did, you would either have that amount or be within a penny of it. So that is finding the required payment for the desired future value of an annuity due. So the big difference in that annuity due was the payment being made at the beginning of each period. We had that extra period's worth of interest, which we accounted for with that interest factor. It's just, notice it is our compound interest factor from future and present values from before with an exponent of 1 because it's only one period.